Hello everyone. So our third class on matrices today. Already we have covered in first and second class the concept of matrix, order of matrix. What are the different types of matrices? How will you identify, how will you decide the number of elements if the order of the matrix is given? So what I suggest before you come to this class, better you go to first and second class where I have covered all these topics, what I explained. And link is given in the description section below for this particular video. Right. So what I'm going to cover today in today's class is product of matrices. This is a very important topic. Product of matrices. A lot of people, they made a mistake whether two matrices can be multiplied or not. It's not like algebra always, right? So this is the second topic I will cover: product in algebra versus product of matrices. These two are not same, right? I will explain that. So let's understand the product of matrices first. Okay. So let's look into this matrix, matrix A. So this 2, 1, 3. What is the order of the matrix? I have explained all these things already in my second class. So order of matrix is how many rows? First rows. Number of rows is 1. Number of columns it is 1, 2, 3. So 1 by 3 matrix. And this one is number of row. It is 3. Matrix B. The order is 3 by 3 rows and 1 column, 3 by 1. If you multiply A with B, that means first A, then B, right? So if you multiply AB, in that case, number of columns in matrix A, it is 3. That is equals to number of rows in matrix B. So if these columns of first matrix, number of columns in first matrix is equal to the number of rows in the second matrix, then only you will be able to multiply two matrix. That is the condition. That is why it is the rule I have mentioned here. The rule is, the first thing is that you need to see whether the product is at all possible for these two matrices or not. If it is possible, then you will go for the second one, how to multiply. Number of columns in first matrix A equals to number of rows in second matrix B. So that is the condition of product of matrices. So when you are asked to find out the product of two matrices, or you are asked to find out whether it is true or false statement, or whether it is possible or not to multiply two matrices, if the order is given or if the matrix is given, you will first task is you need to find out the order of both the matrices. Now if it is asked to find out AB, in that case the number of columns in A should be equal to the number of must need to be equal to the number of rows in column B. If it is BA, in that case the number of columns in B should be equal to the number of rows in A, right? So that is the condition of matrices product. Number of columns in first matrix should be equal to the number of rows in the second matrix. This is the must condition for matrix product, right? Product of AB, it is possible because it is satisfying the condition. Now it is BA. In that case, what is the number of columns? Number of columns, it is 1. And what is the number of rows in A? That is 1. That means AB and BA. Both is possible. Right? So now you will find out how to do the product of matrices. Then I will tell you again why this rule is actually there. Without this rule, you cannot product. Now come to the second point, how to multiply two matrices. Multiply each element of the row wise A. A is the first matrix. Just so you need to remember that multiply each element of the first matrix in this order. In the first matrix, you need to find for each of the row, multiply each element row wise of A, that is first matrix, with corresponding element column wise of B. That means you will take each element of A row wise and then you multiply each element of B with B column wise and you will sum up. Then sum up. So now if you multiply 2, first element of first row with first element of first column, 2 into 1. So it will be 2 into 1 plus second element of first row, second element with second element of first column, 1 into 3 plus third element of first row into third element of first column. So 3 into 5. So what is the result? Result is 2 plus 3, 5, 5 plus 15, 20. So this is just one element. So what is the order of this particular resultant matrix? The result, it is one row, one column. That means it's 1 by 1 matrix. It's returning. So in that case, if we see the row of column 8 is 1, number of column matrix B, that is 1. So that means the resultant matrix will have the row of first matrix by number of column of second matrix. So that will be the order for the resultant matrix. So that is how you need to do. Now I will show you with more number of rows and column also. Right. Now I have changed this matrix B. Still the number of rows is 3, but the number of columns I have increased. I have added one more column, 2, 1, 4. So in that case, what is the order? Earlier it was only 1, 3, 5. So 3 rows, 3 by 1 matrix. Now it is how many? 3 by 2 matrix. So 3 rows and 2 columns, right? Still this is satisfying the condition because the number of columns in matrix A equals to number of rows in matrix B. That means you can multiply. Now what will be the result? See, the resultant matrix, what I have given you the example, the resultant matrix will have the order in that case, the number of rows of the first matrix 1 by number of columns in the second matrix 2. So the resultant matrix AB should have the order 1 by 2. I can do that. This is what it's I will prove it, right? So the resultant matrix will have the order of 1 by 2, 1 row, 2 columns. Let's see. Now what I will do, I will multiply each of the element of this row with each of the element of first column, then each of the element of this row with each of the element of the second column, right? So 2 into 1 plus 1 into 3, first row versus first column, plus third element of first row into third element of first column, 3 into 5. This is the first element, right? What is the second element? Second element will be, then again the same thing you will do with this first row with the second column of second matrix. So it will be 2 into 2 plus 1 into 1 plus 3 into 4. So that is how the matrix will be. So what is the matrix now? It is 2 plus 3, 5 plus 15, 20. The first term, what did I get in the last example? Now the second element is 2 into 2, 4, 4 plus 1, 5, 5 plus 3 into 4, 12. So 17. So now what is the order of this matrix? It is 1 rows and 2 columns, 1 by 2. So that is what we said, right? So if we can multiply two matrices, in that case, the resultant matrix will have the equal number of rows of matrix A and the first matrix and equal number of columns of second matrix. So the order will be here 1 by 2. That is what. So if I generalize this thing, how does it look like? So this is the generalized form. Matrix A, order m by n. Matrix B, order n by p. That means number of columns in matrix A equals to number of columns in matrix B. That means you can multiply these two matrices. Then the resultant matrix AB will have the order m by p, where m is the number of rows in first matrix and p in the second matrix. Okay, so here this is the matrix A, this is matrix B. So you need to find out AB. So you need to find out the order of both of the matrix. If it is AB, order of matrix it is A, order of matrix A it is number of rows 2, number of column it is 3. So it is 2 by 3 order. And what is the order of matrix B? Number of rows 3 and number of columns is also 1, 2, 3. 3 by 3 matrix. So that means your number of rows in number of columns in first matrix equals to the number of rows in the second matrix. I don't care about the number of rows in first matrix or number of columns in the second matrix. Number of columns in the first matrix has to be equal to number of rows in the second matrix. That is the condition for product of matrices. Right? Now you find out the. So what should be the order of the resultant matrix? It should be 2 by number of rows of the first matrix by number of columns in the second matrix, right? So the resultant matrix AB should have the order 2 by 3. Let's see whether it is so. So we will take first row and then again it is with the first column, then it is with the second column, then it is with the third column. For one row, I will expand it. Rest of the cases, I will just verbally say and I will sum up the numbers, right? Multiply and then sum up. So 2 into first element, 2 into 1 plus 3 into 4 plus 1 into 0. 2 into 1 plus 3 into 4 plus 1 into 0. Then second one. So first row with the first column. Each of the corresponding element I have multiplied. Then I will multiply first row with the second column similarly. So 2 into 2 plus 3 into 5 plus 1 into 1. What is the next one? Next one will be 2 into 3 plus 3 into 6 plus 1 into 2. So now I got the first row of the resultant matrix. Now we'll do for the second one, right? So first row multiplication is done, right? Second one is 5 into 1 plus 7 into 4 plus 4 into 0. 5 plus 28 plus 4 into 0, 0. Second one is 5 into 2, 10 plus 7 into 5, 35 plus 4 into 1, 4. And the third element will be 5 into 3, 15 plus 7 into 6, 42 plus 4 into 2, 8. So now you write down these numbers, you sum up the numbers. 2 plus 12, 14 plus 1, 15. First element. Second is 2 2s are 4 plus 15, 19, 19 plus 1, 20. So that is how this matrix. What is the order of the resultant matrix? It is 2 rows and 3 columns. So that is what we said. So resultant matrix will have the number of rows of the first matrix and number of columns of the second matrix. Right? Okay. Now I'm coming to the second topic, product in algebra versus product of matrices. In algebra, what we know, it doesn't work in case of product of matrices. 3 of the basic things I will show you first, right? In algebra, we know if AB equals to BA, that means 2 into 3, 6 equals to 3 into 2. We know that. But in matrix, it is not so. AB not equals to BA. It may be, may not be. So AB not equals to BA, right? What we will check it here. So example, this is the matrix A, this is matrix B. I have just taken both square matrices, but it is applicable for any matrices. So here you need to first check the order of both the matrices. It is 2 rows 2 columns 2 by 2, and it is also 2 by 2 matrices 2 by 2. Now let's find out AB. So what will be AB? Value of AB equals to, so first row of A with first column of B, that means minus 2 into 1 plus 3 into 3. Second one is minus 2 into 2 plus 3 into 5. So first row multiplication with first column and second column, both are done. Now I'll do the same thing for second row. Second row, first column. So 4 into 1 plus 1 into 3. Then first row with second column, right? Sorry, second row with the second column. Second row with first column I have done, second row with second column. So it will be 4 into 2 plus 1 into 5. So what will be the value? It is, so this is what AB. BA equals to, so BA, matrix B first, 1, 2, 3, 5, and matrix A second, minus 2, 3, 4, 1, right? So now let's do the multiplication. So BA, it is 1, 2, 3, 5, minus 2, 3, 4, 1. So multiplication, that's how, same thing. Okay, I'm not explaining further, right? So what is the value? It is 8 minus 2, 6, 3 plus 2, 5, 20 minus 6, 14, and 5 plus 9, 14. So what you are saying? AB, value of AB is this one. Value of BA is this one. Is these two are same? No, these two are not same. So that means what is the relationship here? AB and BA, these two are not equal. So it is not like algebra. Law of algebra in product of numbers, it is not applicable for law of matrix product, right? So AB not equals to BA. That means also it is proven that matrix product is not commutative, whereas rational number product is commutative. So 2 into 3 equals to 3 into 2, or 2.5 into 2 equals to 2 into 2.5. So rational number of product of rational numbers, it is commutative. If you change the order, output result or the resultant product doesn't get impacted for rational numbers. Matrix product is not commutative. So if you change the order, the result will not be same. Okay. In case of algebra, we know that if the product of two variables, is 0, then either of them is 0. So if AB equals to 0, according to algebra, either A is 0 or B equals to 0 or both of them are 0. Right? The minimum condition is any of them are 0. But in matrix, even though you find that AB equals to 0, neither A is 0 nor B is 0. So let's see. So let's say this is one matrix A and this is another matrix B. Now let's multiply these two matrices. So first check the order. It is 2 by 2 and it is also 2 by 2. So you can multiply. Now let's do the multiplication. So it is 0, 0, 0, 0. So it is a null matrix. I have explained it in second class. So in case of matrix null, it is, if it is 0, a matrix is 0, that means it's a null matrix. It is, the variable is 0, one value it is 0 because we can store only one value in a variable, but in a matrices, we can store multiple variables. So if a matrix is set 0, that means it's a null matrix. That means all the element in that matrix, it is 0. So even though AB, that is equals to 0. So if AB equals to 0, here we can see, even though AB equals to 0, neither A equals to 0 nor B equals to 0. So it doesn't satisfy the algebraic law. Right? This one also we have proven. So this is proven, this is also proven. The next one. if AB equals to BC, according to algebra, what we know? If AB equals to BC, then you cancel B, then A equals to C. How will do that? You cancel these two. BB cancel, then A equals to C. This cancellation rule is not applicable for matrices. Product of matrices. Okay? Now, we will prove this third one, law of algebra. Cancellation rule is not applicable for matrix product, right? So let's find out AB first. I'll straight away write down, right? So AB, 4 into 6, 24, plus minus 4 into 3, minus 12. So 24 minus 12, it is 12. 4 into 5, 20, plus minus 4 into 0, 0. So 20. Minus 3 into 6, second row versus first column. Minus 3 into 6, minus 18, plus 3 into 3, 9. So minus 18 plus 9, minus 9. Second row versus second column. So minus 3 into 5, minus 15, plus 3 into 0, 0. So minus 15. So this is the result of AB. Now let's find out AC. So what we can see here we can see that AB equals to AC equals to 12, 20, minus 9, minus 15. So same, AB equals to AC equals to the same, right? But you cannot cancel A. If you cancel A, that means B equals to C, but B not equals to C. So cancellation is not applicable in product of matrices, which is applicable in law of algebra. So these three things I have proven. Now a lot of things that can be proven. Let's say A square minus B square, we know the formula A square minus B square equals to A plus B into A minus B. But if I give you two matrices A and B, you cannot prove that A square minus B square equals to A plus B into A minus B. If I give you two matrices A and B, and I'm asking you whether A plus B whole square equals to A square plus 2AB plus B square, you cannot say that it is. It may not. But algebra rule is not applicable. You cannot apply any algebraic rule in matrix product, right? Okay. Now, if you multiply any matrix with identity matrix, then the resultant matrix or the output matrix will be the non-identity matrix. So here if you see, A is this matrix, and identity matrix I have explained in second class. So this is the identity matrix. So you can see what is the, if I need to do AI, multiplication of AI, then what is the, first you need to check the order. It is number of rows, 2 rows, 3 columns. That means 2 by 3 matrix. And here it is 3 rows, 3 columns, 3 by 3 matrix. So number of columns equals to number of rows. You can multiply, right? Now if you multiply, what will be the result? This one. So which is equals to A. Okay. So if you multiply a matrix with identity matrix, in that case the resultant matrix will be the non-identity matrix, right? So if you multiply even I into A, that will also return the same thing. 2, 3, you can do it on your own. 2, 3, 5, 6, 9, 4. That means what you can say, that A into I equals to A equals to I into A. So product of a matrix with identity matrix is commutative, right? Because if you change the order, then also it doesn't matter. And the resultant matrix is always the non-identity matrix. So few of the properties of matrix product. Few of the cases already I have proven. I have given you the example. Few of the cases you can also prove. You need to remember this, right? It is already proven, right? In algebra, AB equals to BA, but in matrix product, AB not equals to BA. Second one is, if AB equals to AC, according to algebra, you can cancel A, that means B equals to C, but in matrix, B not equals to C. Even though B not equals to C, then also AB and A equals to AC can be. So, if AB equals to AC, it doesn't mean that B equals to C. Maybe, may not be. If AB equals to 0 according to algebra, then obviously at least A equals to 0 or B equals to 0. So either any of them has to be 0 even though both of them are not 0 according to algebra. But in matrix, even though AB equals to 0, product of two matrices is 0, that is returning a null matrix, then also not necessarily either A equals to 0 or B equals to 0. I have proven that already. It supports distributive law. In algebra also we know that A into B plus C equals to AB plus AC. It supports the distributive law, so it is applicable both for addition and subtraction. So A into B plus minus C equals to AB plus minus AC. So either A of B plus C equals to AB plus AC, or A of B minus C equals to AB minus AC. Supports distributive law. Also it supports associativity. That means if you change the group of a matrix, AB into C equals to A into BC. So that is all about product of matrices. So I hope you liked this video, you understood the entire thing. So if you liked it, please click on the like button, and if you want to have this kind of video again and again, because I am always uploading conceptual videos for each of the chapter, each of the topic in mathematics. So if you would like to have this kind of video again and again, please subscribe my channel, Dev's Learning Hub. Thank you very much.